Right now, something weighing 10 million times the mass of our sun is tearing through intergalactic space at 954 kilometers per second. That is 2.2 million miles per hour, fast enough to cross the distance between Earth and the Moon in under 14 minutes. And it is not slowing down. It cannot slow down. The gravitational well of the galaxy it came from has already been left far behind. Whatever this object passes through next, it is passing through alone in the dark, with no home and no destination, carrying a 200,000 light-year trail of newborn stars behind it like a scar drawn across the universe. That object is a runaway supermassive black hole, the first ever confirmed, and the instrument that finally provided that confirmation, the James Webb Space Telescope, did not just photograph it. It dissected the gas around it, measured the velocity of the shock wave at its leading edge, and returned data that left almost no room for an alternative explanation. Peter Van Dokkum of Yale University, lead author of the study and the astronomer who first spotted this object, said, "Something like this has never been seen anywhere in the universe. Here's the full story of how it was found, what Webb confirmed, and why the confirmation is one of the more unsettling things that has happened in observational astronomy in recent years. It started, like so many things in modern astronomy, with an accident. In 2023, Van Dokkum's team at Yale was going through archival Hubble Space Telescope images, searching for star clusters around a completely unrelated dwarf galaxy. They were not looking for anything unusual. They were doing routine catalog work, scrolling through old exposures of the same patch of sky. One of them noticed something in the frame that had no business being there. A streak, a thin, perfectly straight line of light, oriented like an arrow pointing away from a distant galaxy roughly 7.5 to 9 billion light years away. The sight was so strange that the team followed up with fresh observations from the Keck Observatory in Hawaii. The Hubble image captures a moment in time when the universe was roughly half its current age of 13.8 billion years. The first assumption was a cosmic ray artifact. Stray particles hitting a detector produce streaks that can look like real objects. It happens often. But cosmic ray artifacts do not repeat across multiple exposures of the same field. When the teams checked other Hubble images of the same patch of sky taken at different times, the streak was still there, in exactly the same place. It was real. That created a problem. Perfectly straight lines at cosmological scales are not something nature produces easily. Gas clouds scatter. Galaxies spiral. Stellar populations distribute in complex shapes shaped by gravity and rotation and dark matter. Nothing draws a clean 200,000 light-year line across empty space, except something moving in one direction, very fast, for a very long time. The Keck follow-up confirmed that the streak was not a galaxy seen edge-on, not a plasma jet, and not any known category of astronomical object. The spectroscopy showed emission lines along the entire 200,000 light-year length of the feature, consistent with star-forming gas, young stars, and shocked material. The black hole was streaking too fast to take time for a snack. Rather than gobbling up stars ahead of it, it was plowing into gas in front of it to trigger new star formation along a narrow corridor. The structure looked like a wake, and at the tip of that wake, where the emission was brightest and the geometry most concentrated, something was pushing all of that gas ahead of it. Van Dokkum said, "We suspected that this strange object might be a runaway supermassive black hole, but we did not have smoking gun proof." The smoking gun required Webb. Van Dokkum's team obtained JWST NER spec IFU observations targeted at the tip of the linear feature, where a candidate runaway supermassive black hole was proposed to be interacting with the circumgalactic medium of its host galaxy system. The NIR spec instrument, the near-infrared spectrograph operating in its integral field unit mode, did not simply image the region. It took a spectrum of every point within its field simultaneously, measuring how fast every part of the gas was moving relative to every other part. The result was published in the astrophysical journal Letters and is what Van Dokkum described as the confirmation. The researchers measured the blue shift in front of and behind the bow shock and found a dramatic, abrupt with only a thin distance between them. They also found that the gas around the outside edges of the bow shock is redshifted as it streams away. Configuration resolve into a simpler arrangement. One of the three gets ejected, carrying momentum that was effectively stolen from the other two. The remaining pair settles into a tighter orbit. The ejected one leaves the galaxy at whatever velocity the interaction imparted. When the single black hole took off in one direction, the binary black holes shot off in the opposite direction. A feature on the opposite side of the host galaxy in the Hubble images may be exactly that binary, the other half of the recoil. The second mechanism requires only two black holes, not three. When two supermassive black holes in a merged galaxy finally spiral close enough to merge, they emit a burst of gravitational waves in the final fraction of a second before coalescence. If the two black holes have different masses and different spin orientations, those gravitational waves are emitted. The space between and around galaxies is not completely empty. It contains the circumgalactic medium, an extremely thin, diffuse gas of hydrogen and other elements that surrounds galaxies out to great distances. Normally, an object moving slowly through this medium barely disturbs it, but RBH1 is moving at 954 kilometers per second, faster than the speed of sound in that gas. When an object moves faster than the local speed of sound in a medium, the medium cannot get out of the way in time. It piles up ahead of the object in a compressed wall called a bow shock. At the leading edge of RBH1, Webb detected exactly this structure, a dense, compressed region of hot gas being driven ahead of the black hole like a wall of water pushed by the bow of a ship. Behind the black hole, the pressure released by the passage of the bow shock drops. The gas that was compressed and heated as the black hole moved through it begins to cool. As it cools, it becomes denser in pockets and clumps under gravity. Given tens of millions of years, those clumps accumulate enough mass to collapse and ignite nuclear fusion. Stars are born, one after another, strung out. Along the 200,000 light-year path the black hole has already traveled. Like sparks trailing behind something dragged fast across a rough surface, these are not stars in any galaxy. They have no home. They will drift as rogue stars in intergalactic space indefinitely, orphaned by the same event that produced them. The confirmation of RBH1 closed a prediction that had been sitting on the theoretical books for roughly 50 years. Van Dokkum said, "This is the first confirmation of a runaway supermassive black hole, following 5 decades of theory and research about these objects, but the confirmation arrived with an immediate uncomfortable implication. RBH1 was detectable only because it happened to be moving through a patch of gas dense enough to produce a visible bow shock and a star-forming wake. If the same object were moving through a sparser region of intergalactic space, none of those features would exist. No bow shock, no star trail, no streak, no detection. The black hole itself is invisible. The event horizon absorbs all light. What Webb saw was not the black hole at all. What Webb saw was the gas and the stars and the shock that the black hole's passage created around it. In 2025, several papers showed images of surprisingly straight streaks of stars within galaxies, suggesting runaway black holes may be more common than previously assumed. One describes a long, straight contrail cutting across a galaxy called NGC 3627, likely caused by a black hole of about 2 million times the mass of the Sun, traveling at 300 kilometers per second, with a contrail about 25,000 light-years long. Multiple runaway black holes identified in a short period in different galaxies at different mass scales suggest the process is not a rare anomaly. It is a natural consequence of galaxy mergers. And galaxies have been merging throughout the entire history of the universe. Van Dokkum said, "The obvious next step is to look for more examples." The Nancy Grace Roman Space Telescope, scheduled for launch in 2027 and designed to survey large areas of the sky at high sensitivity, is expected to dramatically expand the catalog of candidates. What RBH1 established is that the signatures of runaway supermassive black holes are visible and recognizable when the conditions are right. The question that remains open is how many are out there in conditions that are not right for detection, moving silently through the sparse voids between galaxies with nothing to push against, invisible, undetectable, and entirely unaccounted for in any existing model of how much mass the universe contains in forms we cannot see. Van Dokkum put it plainly, it boggles the mind. The forces that are needed to dislodge such a massive black hole from its home are enormous. For 50 years, the runaway supermassive black hole was a prediction, a theoretical consequence of galaxy mergers, written into the mathematics of gravitational dynamics and confirmed in simulations. It was a reasonable prediction. Nobody doubted it was probably real. And then Webb pointed at the tip of a streak that Hubble first noticed accidentally in 2023, and the data came back, and the velocity jump was 600 kilometers per second across a single kiloparsec, and the question was settled. It is real, it is moving, and it is not the only one.